All right. Welcome to day 2 of chapter 12, inference for linear regression. All right. So to start off with on our inference for linear regression, we're going to do another problem here working with what we did in the last class just to make sure we're okay. And then we'll proceed to what we do when we have relationships that aren't linear and what we can do to transform them to be linear. Okay, so here we have the situation with these babies and their cry counts and trying to see if there's a relationship between how often a baby cries when given a stimulus that should make them cry and the IQ score later on. Okay, so we have all this data, and this information comes from a random sample of 38 infants. Okay, so if we ask the question, what is the equation of the least squares regression line for predicting IQ at age 3 from the number of crying peaks, known as the cry count, and to interpret the slope in the y-intercept of the regression line in context, well, we'd be able to say, hey, on these coefficients, that's what we're looking for. So y hat, remember the hat, 91.268 plus 1.4929x. But remember, if we're going to use this y hat and this x, we need to define them. So y hat's going to be the predicted IQ. It must say predicted. And x is going to be the cry count. That's what we're calling it, right? In the peak crying, how many times did they cry? Okay. And what's the interpretation? Well, if the baby does not cry, then the IQ predicted is about 91. Right? That is that if x is 0. Right? If x is 0, no cry, IQ 91. Right? And then for the slope, for each additional cry peak, the regression line predicts an increase of 1.5 IQ points on average. Right, so it seems to be that there is a little bit of a positive relationship between having a stimulus, an external stimulus to make you cry, and how actively the baby cries, right? And there's a lot of research into this, child psychology and other pieces, to kind of see, hey, what can we do to help parents and children be better? Okay. Then explain the meaning of S in this setting. So we look up here and we have this value of S, and we want to know, what does that mean? Well, in this setting, S is the standard deviation of the residuals, right? So therefore, the typical prediction differs from the actual IQ by 17.50 points on average. Right? Why do we say this? Well, the prediction minus the actual IQ, that is my residual, right? Remember that my residual is y minus y hat, right? Y minus y hat is my residual. And so any particular value, right? The standard deviation lets me know the variability of a particular value from the average value, right? And so that's what we have. Okay. If we continue on with these questions, right, then it comes over here and it says, hey, let's determine if there is convincing evidence of a positive linear relationship. Okay. This really would be the question in and of itself. I've taken to break it out so that you understand each step a little bit better. Okay. So L, do we have a scatter plot that's linear? All right. So I come over here. Which one of these is my scatter plot? Oh, here is my cry peaks to the IQ score. So this is my L. And it's kind of weakly linear, but it does seem to be positive and maybe linear. So that's our L. Okay. I, this is not an experiment, so we must meet the 10% condition. So we need at least 10 times 38, that's 380 babies in the population, right? Most likely that the babies are all fairly similar wherever they're coming from. And so we would say that, yes, that's a reasonable expectation, right? And so over here, the 38 infants, this is going to be for our I. Okay. N, the normal plot, right? Do we have normality? We don't have a histogram of the residuals. So we have to look at our normal plot, the expected z-score versus the residuals, also known as a QQ plot, right? And that does seem to be pretty linear, right? If we look over here, we seem to have pretty linear, right? And so this is where we're talking about our normality, okay? E, the variability of the residuals is not unusual. We have an equal scatter about 0, right? What does that mean? If we look at this residual plot right over here, right, there's really no pattern in the residual plot, and regardless of the cry count, seems to be spaced out up, down, about the same amount across that line 0. So that is E. And then finally, R, a random selection, right? We do have our random selection. And so there, then we have the liner we have to talk about, L-I-N-E-R. Got to be able to talk about each of those items, okay? So if all those conditions are met, now we can do a t-test for beta, the true slope of the linear regression. All right, so then state the type of test. Well, t-test for beta, right? The population slope, right? And appropriate hypotheses, right? We want to know, hey, is there convincing evidence of a positive linear relationship? So our null hypothesis is going to be that there is no relationship, that beta is 0. And the alternative, right, is going to be that beta is positive, because that's what we're trying to figure out. We're going to use alpha as 0.05. Okay. Then our next step in the solution process, the value of the test statistic, English is hard for me, sorry, is provided in the computer output. Verify the value of the test using the computer output and state the p-value with reasoning. So let's look at this computer output here. Okay, if we look at the computer output, here we are. This t-value shows us 3.07. This p-value shows us 0.004. All right, so let's go through here. It says to verify. So verify means, hey, kind of show me how you would get that answer using the computer output. Well, that 3.07 is the test statistic. It's going to be the statistic minus the parameter over the standard error of the statistic. Where do I get that information? I get that information from right over here. All right, we know this sheet, very important. And I come right over here and I see, oh, hey, look, standardized test statistic. Here's what I have. Very important. Okay. So I've got that, and that's going to be that 1.429 minus 0, the standard error of the statistic. Where did I find that? So once again, here is the standard error. Here is my p-value. That is my statistic, right? And of course, my p-value. So I have each of those, right? And that gives me, whoops, excuse me, right? That gives me that 3.07. And the p-value for the cry count is listed as 0.004. However, this was a one-sided test. So the p-value is actually 0.002. That's an important distinction, right? That column P does stand for p-value, right? The probability of getting something at this level or further. And that p-value comes from column P. That's very important that it always lists it as a two-sided p-value. When it's one-sided, divide by 2. Okay. What would be our conclusion at the 5% level of significance? Well, this is fairly standard. We're used to this. Because the p-value is less than alpha, we reject the null. There is convincing evidence of a positive linear relationship between crying intensity and IQ score for our population of infants. You know, this might not be true the world around. This might not be true region by region, but for the population of infants that we work with, it seems to be true. Okay, and then this last one I added in because it's an important concept. Determine the test statistic if the null hypothesis was instead that beta is at most 1, right? Well, if the parameter is 1, that's what this is stating right here, then we would have, hey, that t is equal to 1.4929 minus 1 all over 0.4870, right? Because we have the statistic, the parameter, the standard error, the statistic, and that gives us 1.012. And hopefully, as you're starting to understand these items that have our normal distributions, you kind of need to be with the t-value more than 2 before it's going to start to be in the reject the null hypothesis region. Of course, if we're more than 3, we're most likely rejecting. Okay, so hopefully that information makes sense. All right. This is Frankie back from when I lived in Sleepy Hollow area. The wife used to work in Sleepy Hollow. That's at the Sleepy Hollow Cemetery a few Halloweens ago. Love the photo. I hope you're having a great time.